Hello, everyone. Welcome to another wonderful day of chemistry. So, we're starting a brand new chapter where we're going to be looking at phase changes. Specifically, we're going to be looking at pure components. And so, really, the major thrust of this chapter is going to be taking a lot of the thermodynamic properties we saw in the last two chapters, especially this ideas of spontaneity, and trying to apply them a little bit more explicitly to phase changes. But before we do this, we need to kind of go over a lot of terminology because it turns out physical chemistry has some very specific uses of terminology, and some of these are going to be words that you thought you knew that have a slightly more nuanced or specific meaning. So we'll start with a good phrase we've been dealing with so far, and that's going to be state. So again, when we're talking about the state of a material or the state of a mixture, what we're looking at is more or less kind of the sum of all of their physical properties. And these are going to be defined by the state variables. So we have our major ones that we saw all the way back in ideal gases, volume, moles, which together give us molar volume, pressure, and temperature. And the idea is if you know all of these state variables, you can definitively define the state of the material and all of its physical properties. Now, one of the big ones we're dealing with is going to be phases. And so the idea of a phase is it's going to be a uniform a description of of a material that is uniform in chemical composition. So that means it has the same exact composition all the way throughout, and its state is the same all the way throughout. So we're not talking some heterogeneous mixture where there's pockets of hot or cold or different densities. This is going to be a very homogeneous thing. Now, one of the important things to keep in mind is when we're looking at different allotrops, these are going to count as different phases. And as a reminder, allotropes are essentially different kind of solid crystals of the same material. The classic example being diamond and graphite, where both of them are just pure carbon, but they have very different crystal structures, so they have very different properties. And so this is going to be very important to keep in mind, is that you may have, say, a solid material, but it may compose of several different phases if it is, again, non-uniform. And that's important to keep in mind. The next major one, this is going to become a little bit more important as we move into the next chapter, looking at mixtures, is going to be constituent. And this is a chemical species that is present. So, for example, this is going to be any independent kind of molecular form, whether it's ionic like sodium or chlorine, or a composite like water. So each of these can essentially vary in composition. And so these are going to be chemical constituents. And we need to make sure we keep constituents different from components. And my apologies that they're both C's. And a component is going to be a chemical constituent that is independent. So for example, I may have sodium and I may have chlorine, but if I know the sodium concentration, I know the chlorine because they have to be 1-to-1 because of charge balance. This gets a little bit more complex when you have different mixtures of cations and anions, but they will essentially be constrained by that charge balance. And so we have to be very aware when we're dealing with these species of whether we're talking about constituents or components, because this can make a big difference. Now, because we're looking at phases, one of the other important things we have to deal with is phase transitions. So this is going to be any point at which multiple phases are present simultaneously. So one of the classic ones is being melting point, also known as in the reverse fusion, where you have both a solid and a liquid. Now, one of the important things to note is, especially with pure phases, the temperature doesn't tend to change while you're undergoing that entire phase transition. Now, because we like mathematical descriptions, we're often going to describe these phase transitions with phase boundaries. So these are going to be lines which can be described, not surprisingly, by equations that denote when I transition from one phase into another. Now, one important property for this is going to be something called the vapor pressure. And the vapor pressure is going to be the partial pressure of a gas above a liquid mixture. Now, the important phrase here is equilibrium, because this is going to be the partial pressure of the partial pressure of the gas when it has essentially reached saturation, where I can't put any more of the liquid into the gas phase without it condensing right back out. So this is an important idea. This is going to be the maximum pressure of the component in the gas phase. And this is where it's important to note that we're looking at thermodynamic properties, which says where is the system at equilibrium? We're not looking at kinetic properties. For example, we often have water vapor that is much less than the saturation level, just because while water is evaporating, it isn't evaporating quickly enough to saturate it. So it's important to note this ends up setting a maximum, but in many small closed contain systems, you can often hit that vapor pressure. Now we have another important point here, and this is going to be the boiling point. So the boiling point is essentially going to be the temperature at which the vapor pressure, so this maximum pressure, equals the external pressure. Because the idea here is once that happens, what we're going to have is that the liquid will then try to essentially go all the way into the surroundings, and and the component will no longer be constrained in the liquid phase, meaning it escapes. And this is really what happens when you boil a pot of water. I encourage you to do this. You'll see these bubbles form, and those bubbles can now push the water out of the way and escape. And this is the important part of the boiling point. And note, the boiling point is defined based on the external temperature, or external pressure. And this is one of the reasons why it's very important to make sure we define our external pressures. And this is why we like to denote whether we're talking about normal boiling point, which has a pressure of 1 atm, or the standard boiling point, which has a pressure of 1 bar. Because it turns out those temperatures differ by about 0.4 Celsius. Not a huge difference, but enough to make a significant difference. Then we have our melting freezing temperature, and this is going to be the temperature at which a substance melts. Again, this is often known as the temperature of fusion. And thankfully, this tends not to change quite so much because, as we'll see later, melting and freezing is going to be much slower to change with external pressures. So it's going to be relatively fixed. Now we have our last important points, and these are going to be the critical pressure and temperature, which we've seen before. This is the point at which a liquid and gas are going to start to form a supercritical fluid. And again, this represents the minimum temperature and pressure combination. And then we also have an important point here, and we'll talk more about this throughout the chapter. And this is the idea of the triple point. And a triple point is the exact point in time, point in pressure and temperature at which the liquid, the gas, and the solid are all present. And to really kind of understand the triple point, we really need to use something called the phase rule. And what the phase rule is, it tells us where we are on a phase diagram based on how much freedom you have in defining the phases present. And so we could define this with a simple equation where F, which is going to stand for the variance. So this is the number of state variables that can define the system. So remember, when I'm looking at an ideal gas, we say this can be defined with 2 parameters. So if I know the pressure and the temperature, I can find the molar volume and perfectly know my system. Now, it turns out the variance is going to depend on how many components I have in my system. Am I just a 1 component system, or do I have 2 components? Say like a simple model of the atmosphere where it's mostly oxygen and nitrogen. Then we add 2, and then we subtract out the number of phases. Because every time I add in a phase, that constrains the system, and it eats up one of these degrees of freedom because it defines how these 2 phases are in reliance to each other. More or less, it gives us an additional equation to constrain the system, which eats up a degree of freedom. So let's say we're looking at a pure gas like CO2. So previously we've said I can define any ideal gas with 2 variables. Let's go ahead and prove this. So if I have a pure gas, I've got 1 component, and because it's a gas, that means I only have 1 phase. So I've got 1 plus 2 minus 1, my variance is 2. So I can perfectly define the system with my choice of temperature, pressure, and molar volume. Pick 2, you've defined the system. Now, this is fairly useful when we're looking at single component systems, and we'll make use of this in a second. But where this really is going to come into play is when we have mixtures, where we have multiple components, and we know exactly how many variables I need to know to define the system. And that's going to be really the focus of chapter 5, is when we're really going to be diving into these mixtures. Now let's go ahead and really kind of make use of this phase rule by looking at a phase diagram. So here's a classic phase diagram for CO2. And we can apply these ideas. So again, if I have a gas, remember I can define the system based on the pressure and the temperature. Because what we can do is we can move around freely in this two-dimensional surface as long as I'm a gas. And we can do the same thing for any of our pure phases. Same thing with a solid. If I have any pressure and temperature, it can land anywhere in this region and still be a solid. Same thing with a liquid. It moves freely in pressure and temperature. But let's say I've got two phases simultaneous. So let's say I've got a solid and a gas, at which point I've got a sublimation reaction, where the solid is subliming into a gas, which is depositing into a solid. So these two systems will be in equilibrium. And notice that as in this range, my variance now drops to 1, because if I define the temperature, I immediately know the pressure. And that will be true anywhere in this line. So this is one of the reasons why we love these phase diagrams. And we love our phase equilibria is because now instead of having to have multiple variables, as long as I know two phases are present, I can perfectly define a system. And it is worth noting, this is often something that's used when you're trying to calibrate a temperature probe, because you can use, say, the boiling point and the freezing point of water. And if you know the pressure, 1 atm, congratulations, you automatically know the temperature, and you can use that to calibrate a thermometer. It's very nice. And again, so we'll notice we have this for the sublimation, which again will also have its own vapor pressure. And the same thing with the liquid and the solid. All of these will be defined by single variables as long as you're on the line. Then we get to our favorite point, the critical or the triple point, where notice when solid, liquid, and gas are all simultaneously present, this is now defined by being a single variable, or by having no variance. So if I know all three phases are present, which by the way happens for most substances at their freezing point, there is often an equilibrium vapor pressure. You now perfectly know the pressure and the temperature, at least the pressure of the gas. And that is actually fairly cool. And we really do enjoy making use of the triple point because it is one of our best reference points in defining a system. The other point which we've used so previously is the critical point, because this is also where we're in equilibrium in between the liquid, the gas, and now our supercritical fluid. So both of these 2 points define important reference points that will not change and can be used to help build up these lines as a useful reference point. Now, a fairly fun thing, as long as we're talking about phase diagrams, when we're looking at CO2, notice that you can form a supercritical fluid at relatively low temperatures and relatively low pressures. This is very important because it turns out that supercritical CO2 is going to be a nonpolar liquid that flows like a gas. And it turns out that means it's very good at absorbing other nonpolar compounds. And as a result, if you've ever gone to get your clothes dry cleaned at a industrial dry cleaner, what they're using is supercritical CO2. Or if you like me to drink decaf, they remove the caffeine using supercritical CO2 to pull off the caffeine. And it's a fairly fun feature. So this goes ahead and lets us look at a lot of the major properties we're interested in for phase transitions. We have our phase boundaries, we have our phase regions, And we now know how to predict the amount of variance that we have in a system. Now, next time, we're going to be trying to apply some of these concepts to one of our favorite materials. Next time, we're looking at water. Until then, take care.